G'day, welcome to our last lesson on our atomic structure unit, where today we are looking at the concept of ionization energy and its trends in the periodic table, where our lesson objective is to understand ionization energy and use this to rationalize trends in the periodic table and to deduce electronic configurations of elements and to interpret ionization energy data. So we've been talking a lot about a lot of sort of fundamental concepts to chemistry, the idea that the electron has orbitals and it exists in subshells and there's discrete fixed energy levels that the electrons can exist between for any given atom. What we're going to look at today is sort of discussing what the evidence for all that being true, what evidence there is, and what that evidence can tell us about the atoms that we have. So evidence is the name of this slide. Where does the evidence come from for fixed energy levels? So what scientists have done is they've removed the electrons by firing a high-speed electron beam at the atom, and you can remove the electrons from a given atom and you find some interesting sort of phenomena occurring. What this can do is this determines the ionization energy, which is exactly what it sounds like, the energy needed to ionize it. Now it's going to be ionized because we're removing electrons. So if we're removing electrons but the protons number is staying fixed, we're going to be forming cations. So the energy to ionize something. But let's do a good definition instead of me just winging one off the top of my head. The energy needed to remove 1 mole of electrons from 1 mole of atoms of an element in the gaseous state to form 1 mole of gaseous ions is the ionization energy. So we can see these fixed energy levels through something called atomic emission spectra, which again is just kind of what it sounds like. It's a spectra that you get from the emission of energy in an atom. Where essentially you get a spectra of light which has characteristic fingerprint wavelengths for any given element. Discrete photons characteristic of the electron jumping the energy levels. So what do we mean by that? Let's think and consider that we've got an atom. We've got a nucleus, we've got quantum level 1, quantum level 2, and quantum level 3. Let's just take a simple hydrogen atom where we've got 1 electron. If I were to excite that electron with the correct amount of energy so that it could jump between the energy levels here, what the electron would do, it would be in an excited state. It would absorb that energy and then it would go to a more higher energy quantum level. But eventually it will want to lose that energy, so it can go back down and lose that energy and go back down to the original energy level that it was in. But what happens is it loses this energy in the form of a photon, a light. Now because this is a very specific energy level, this light that it loses will have a very specific wavelength. So depending on what electron energy levels you have in an element, you will have the photons being given off unique for that element, and you will end up with a very characteristic emission spectra for that element. So you'll see just the specific wavelengths of light that are given off when these electrons move between the energy levels. And then under here I said you can use this analytically to determine what element it is, because they will be characteristic, because the number of protons and the number of neutrons and the number of electrons in any given element is different. So these energy levels are all going to be slightly different from one another depending on what element it is. So why this is evidence for the electrons being in fixed energy levels is because if you could have an electron at any energy level, you would expect the light that would be given off to correspond to essentially every frequency of light, of the visible spectrum I should say, as it moves down between the two levels. But that's not what's observed at all. What you observe is just these very specific bands of colored light. I might use a colored marker. So say in this case, if we've just got 1 electron and we've just got 1 energy level we're moving for, between we would just see 1 photon of light that corresponds to 1 specific wavelength. So this gives us evidence, and you can see this for all the different elements, that there are fixed energy levels that these electrons are existing between. But let's talk about this ionization energy. So what we're talking about now is we're knocking the electron completely out of the atom to form an ion. And you can do that as many times as you want if you've got enough energy. You can knock 1 electron out, then you can knock another electron out and get a 2+ ion, another electron out, get a 3+ ion, another electron out, get a 4+ ion. It takes more and more energy each time, as we're about to see, but you can do it. So ionization energy has this symbol delta Hi. Now, delta Hi is a measure of what's called enthalpy. And you can just use enthalpy and energy synonymously as far as we're concerned. It's a measure of the energy that is in a given system. So that's what this H is, that's the enthalpy. I for ionization, you might have worked that one out. And this delta sign, you see this a lot in physics and probably in maths too. This just means a change. So the change in energy, in this case, the ionization. So there's going to be all sorts of subscript symbols to represent different types of enthalpy, but we're just focusing on the ionization energy. So it requires energy to knock the electron out of the atom. Therefore, it is an endothermic endothermic process. So let's consider that first part. Requires energy to knock the electron out. We've been talking about the idea that opposite charges attract. We have a positive proton, we have a negative electron. They're being electrostatically attracted to each other. Now, it might just be a weak electrostatic attraction, or it can be a very strong electrostatic attraction, depending on how close to each other they are. But if we want to overcome that electrostatic attraction, we're going to have to put energy in to overcome that attraction. So it's always going to be a process that takes energy in order to ionize. So we call this an endothermic process. Now, two words that you might or might not have seen before, but you're going to see a lot more of in the coming lessons: endothermic and exothermic. Endothermic refers to when energy is absorbed from the surroundings. When energy is absorbed from the surroundings, it means that the surroundings is losing energy. So say you've got a beaker where you've got an endothermic reaction in. The endothermic reaction is taking that energy, and consequently you're going to feel the beaker get colder. So endothermic reactions get colder, whereas exothermic reactions are the opposite. Exothermic is when energy is released to the surroundings. So in that case, they're letting off heat. So if you've got an exothermic reaction in the beaker, you'll feel the beaker get warmer. Now, in terms of their delta H, a endothermic has a positive sign, and exothermic will have a negative sign. So you can determine from this delta H very quickly, depending on the sign, if it's going to give off heat or take in heat. Why they're positive and negative, that is something we are going to be looking at in future units, not right now. All we're introducing right now is this idea of the endothermic and exothermic terminology. So let's do a general chemical equation to represent this ionization energy. Here we have the ionization energy, delta HI, for the first ionization energy. So like I said just before, you can have subsequent ionization energies. You can take one electron out and get a 1+ ion, and you can take another electron out, get a 2+ ion, another electron out, get a 3+ ion. And we can show all of these with chemical equations. So we have X. X is in any element. X means the unknown element. There's no element on the periodic table that has the symbol X. So whatever our element is in the gaseous form, because we said that the ionization energy is defined by the atoms and the ions being in the gaseous state. So we show that gaseous state. We knock one electron out and we end up with a 1+ ion in the gaseous state and a mole of electrons. The second ionization energy, delta H ionization energy 2, well, we've already got an X+, so now we're starting with an X+, because we've knocked the first electron out in this delta HI1. Now we've got the 1+, we knock another electron out, we get a 2+, a mole of the 2+ gaseous ions and another electron. Delta HI3, now you got the 2+ ion and you're making the 3+ ion. Then delta HI4, you can probably see where this is going. You got the 3+ ion and you can make the 4+ ion. And essentially you can keep knocking electrons out until you don't have any electrons left. It's going to take more and more energy to do that each time, but you can do it. Need to supply more energy each time an electron is removed because of that electrostatic attraction between the positive nucleus and the negative electrons that you have to overcome. Let's look at this graphically with a specific example. We have sodium here. Electron configuration 1s2, 2s2, 2p6, 3s1. For a refresher on electron configuration, see the previous video in this series. But we could tell this is sodium without having any of this information, because we have 11 ionization energies down the bottom. That implies to us there are 11 electrons available to be knocked out. The element that has 11 electrons is sodium, because once you've knocked out 11 electrons, there's no more electrons that you can knock out after that. So you can determine how many electrons there are by just seeing how many numbers you go up to down the bottom. On this side, we have the logarithm of the energy. Now, the logarithm just makes all these numbers a little bit closer together, because as you have successive ionization energy. It takes more and more energy each time to knock out successive electrons. Let's think about it. You have an atom, you knock out one electron, you have a +1 ion. That now has more protons and electrons, so that nucleus, that positively charged bit, is going to hold those electrons more tightly than it did before. You've now knocked out another electron. You've got a 2+. You've got more positive charge for that negative charge. It's going to be held even tighter. You knock out another one, you've got 3 positive charge. So the more you make that positive and negative charge out of balance, the harder it is to then get another electron out. So the energy differences become so massively different that we put it on a logarithmic scale to show the trends a bit more easy. Okay, let us draw a sodium atom that we can play along with whilst we go through this graph. So I got a nucleus in the middle. I got not subshell, quantum level 1 with 2 electrons, quantum level 2 with 8 electrons. We can work this out. Remember our 2n squared rule. 7, 8. And then sodium, I've got 1 electron in that third shell. All right, I fire my electron beam. I get rid of the first electron. Nope, not like that. Like that. Oh, any second, there we go. Takes so much energy. It takes 495.85 kilojoules per mole. So kilojoules is a unit of energy. It takes that much energy for each mole of the sodium gas that you have. So we have the delta H of ionization 1, the first ionization energy of sodium. So remember, 1 mole in the gaseous form to form 1 mole of gaseous ions and 1 mole of electrons. On my diagram, I knock that one out and form a 1+ ion where we've got 1 extra proton, then we do the electrons. So what you might see from here is there's now no third quantum level. So we are now going to take our next electrons from the second principal quantum level. And that looks like this. If you follow along up here, you can see the 2p shell going down, consequently with each of those. Now what's interesting about this is all of our electrons in our second quantum level have a similar increase in energy across that quantum level. Whereas if you compare that to our first quantum level, we see a big jump. And that makes sense if we think in terms of fixed discrete quantum energy levels, because there is going to be a big jump because these are a fixed energy distance. They're a fixed, fixed energy levels away from each other. So what you might see, or what you might expect to see now that we've gotten rid of all of these 2 electrons, is we see another jump as we now have to take them away from that first quantum level, that closest quantum level, and this is going to take the most energy of all. And in fact, that's what you do see, energy level there and energy level there. One other thing to note, though, is that you still do see a general increase across a quantum level, because remember, as you take out each electron, the subsequent one becomes even harder, so it takes more energy. But there are these big gaps between the quantum level, which is what we're interested in. So look up here, I've color-coded my quantum levels, quantum level 1, quantum level 2, and quantum level 3. We can see that the 3s1, the outermost electron, is the easiest to get rid of. It takes the least amount of energy. Then you have a big jump between the third quantum level and the second quantum level, where we've got our 1, 2, 3, 4, 5, 6 2p electrons, and then our 2s electrons. And then we see the jump between the quantum level again, where we have our 2 1s electrons. Let's look at what factors affect the ionization energy. The first one is the size of the nuclear charge. Ionization energy increases as the number of protons increase. The more protons you have, the more energy you need to overcome that electrostatic attraction between the protons and the electrons. The distance of the valence electrons to the nucleus. The further the valence electrons are from the nucleus, the lower the ionization energy. So the closer the positive protons and negative electrons are to one another, the more energy it's going to take to overcome that attraction. And the third one is the shielding effect of inner electrons, which is just what it sounds like. Shielding, you think of shielding in your everyday vocabulary to mean sort of protecting. As the number of electron shells between the nucleus and the valence electrons increase, the ionization energies decrease. So what that means is that in an atom, if you've got these electrons that are in the inner shells, these electrons are sort of shielding, they're blocking these outer electrons from the effect of that positive nucleus. So this shielding effects makes it easier for the electrons out here to be taken off because they're having less of an impact from the positive charge of the nucleus. As the number of electron shells between the nucleus and the valence electrons increases, the ionization energy decreases. What if we were to do it the other way, where we're given the ionization energy data and we have to determine the electronic configuration of the element? Well, we have an unknown successive ionization energies of a particular element here. Straight away, we can see there are 4 very clear energy levels between these electrons. So this is going to tell us that it has 4 quantum levels, so therefore it's going to be in period 4. The first electrons that were taken off, we've got 1, 2 electrons in the outermost shell. That's going to tell us that it's from group 2. So then we could look on the periodic table, period 4, group 2, that is going to be calcium. We could also determine, because we have 20 electrons here, we have 20 ionization energies, so there's 20 electrons will be calcium. So if we had to do the electronic configuration, we have the 2 innermost 1s2 electrons, then we have 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 1, 2, 3p6, 1, 2, 3, 4, 5, 6, and then 4s2 there. So remember, you're taking the electrons from the outermost shell first. So when you're doing the electronic configuration, you've sort of got to read it backwards because the last electrons coming out are going to be the ones that are closest to the nucleus. What if you weren't given the graph at all? You were just given the raw data of the ionization energies. We're asked, what group is this element in? If given successive ionization energies, find the first big gap. This will tell you the number of electrons in the valence shell. Can expect the first 2 to double without counting as a gap. All right, so the first ionization energy, we have 1300, then we have 3300, 5300, 7400. So we're increasing by about 1200 each time. There's been no big gap yet. Then we got about 11,000, 13,000, 71,000. So this is our gap. So this tells us that we have 1, 2, 3, 4, 5, 6 electrons in our valence shell. And then after 6 electrons have been removed, we have our first big jump into the next shell. So if we remove 6 electrons in the valence shell, that's telling us this is going to be in group 6. So by determining the first big gap, you can determine what group the element is in. Okay, that concludes the first part of this lesson where we're looking at the ionization energies of specific elements when we're doing it successively. Now we're going to look at trends in the periodic table. So what happens when we compare the first ionization energy of hydrogen to the first ionization energy of helium, to lithium, beryllium, boron, carbon, nitrogen, oxygen, etc., etc. What it looks like is it looks like this. Now, your first glance at that, you might go, well, that's just a whole bunch of random lines. That's not doing anything. But if we look at this closely, we can actually see lots of trends that tell us lots about our understanding of the electrons. All right, let us draw the electronic configuration of each atom. So I'm going to flip over to the board. We're going to draw it this way, where we've got energy there, and then I'm going to have my energy levels 1s, 2s, 2p, 3s, 3p, I'm going to try to keep this straight, 4s, then we have, nope, we'll just stay there, that's all we're going to do. So our first one, hydrogen. We have hydrogen and helium. So hydrogen has 1 electron in the 1s, helium has 2 electrons in the 1s. Question. Why is the delta H of the first ionization energy higher than helium than it is for hydrogen? We've got to consider these factors that affect the ionization energy. So the factors are the size, where can I write this? Size of the nucleus. It is the distance from the nucleus. And then it is the effects of shielding. All right, so in the case of hydrogen and helium, they are both in the same quantum level. So the distance from the nucleus is the same. they have no shielding effects. There are no electrons that are between the nucleus and the valence electrons for a hydrogen or a helium. So what we can see here is that our helium is going to have a higher ionization energy than hydrogen because it has more protons, because the nuclear charge is increased. Higher nuclear charge, the more energy it takes. Then we see a big drop from helium to lithium when we see the first ionization levels of lithium and beryllium. Why? Let us consider lithium. So lithium is going to be 1s2, 2s1. So if I were to draw a lithium atom down here, what we can see is that we've gone and put in another quantum level. So we've increased the distance that this valence electron is from the nucleus. So therefore, if we're going to remove this electron and the distance is increased, it's going to take less energy. We've also, for the first time, got effects from shielding. So we have an inner shell electron, or two inner shell electrons, that are essentially blocking that nuclear charge from that valence electrons, so it makes it a little bit easier for the electron to be removed. Or I guess if we look at the graph, I mean, that might be considered as a lot easier. But then we see an increase to beryllium. Why would we see an increase in beryllium? We haven't changed the distance from the nucleus. Both these electrons are in the same quantum level. The shielding, they've still just got one inner shell. We have increased the size of the nucleus. Then we get our electrons that have 2p as the valence shell. We see a general increase. The general increase we see because of the size of the nucleus is increasing. The distance of the nucleus and the shielding is staying the same for all the 2p subshell. It's just the size of the nucleus is getting bigger, so it is going to take more energy to remove them. But we do see something interesting in here. We see nitrogen having more energy than oxygen, and that sort of goes against the trend. But we can use what we learned last week to rationalize that. If I were to draw the electron config for nitrogen, which is number 7. So I got 4 there, 1, 2, 3, 4, 5, 6, 7. So that's nitrogen, and then oxygen is 8. So oxygen has 1 extra. What we discussed last lesson was this idea that full shells and half full shells, or full subshells and half full subshells, are stable arrangements. Nitrogen has nitrogen has a half full subshell, so that's quite a stable arrangement. And it turns out that being half full is more stable than oxygen having, even though oxygen has a bigger nucleus, this is less stable than that one was. If it's less stable, it takes less energy to remove it because it's not as stable. So that's what we see in this part here because of that half full P subshell. So what do you predict is going to happen? We get all the way up to neon. Noble gas has a full valence shell, very stable. We're now increasing the quantum level as we go to sodium. So we see another big drop the same way that we did between helium and lithium. And that is because we are now adding another quantum level. If we're adding another quantum level, we're increasing the distance from the nucleus, we're increasing the shielding, therefore it's going to take less energy to get rid of that first electron. We then increase the nuclear charge, so it's slightly bigger for magnesium. And then we see the 3p electrons here having the same trend as the 2p electrons. And we also see the same thing happening where we have the half full 3p subshell for phosphorus being stable, and consequently the sulfur taking less energy to ionize, similar to what happened with the nitrogen and the oxygen over here. Then after the 3p, we enter our fourth quantum level. So we again see another big drop as the shielding and the distance from the nucleus increases. The last thing to talk about here is the same way that we have drops of energy between quantum levels, we also see drops in energy between subshells for the same reason. So as we go from this electron in the, let's say the beryllium one here would correspond with the 2s electron. Our boron now has a p electron in its outermost shell. So we jump a much smaller energy level compared to the quantum levels, but we're still jumping an energy level. So we see a slight decrease in the energy between the s and the p orbitals. So between the 2s and the 2p orbital and the 3s and the 3p orbital. And that concludes our lesson and also concludes our unit on atomic structure. What have we done today? We have explained and used the term ionization energy, explained the factors influencing the ionization energies of elements, explained the trends in ionization energies across a period and down a group of the periodic table. We have deduced the electronic configurations of elements from successive ionization energy data. And finally, interpreted successive ionization energy data of an element in terms of the position of that element within the periodic table. As always, if you pause the video now, here are some tasks you can do that will help you consolidate the concepts that we've covered in today's lesson. Excellent, well done. We will be starting Unit 3 in the next video. Until then.